So here in section 11.2, we're actually going to fit our model. So we're going to find our least squares regression line. So remember, our deterministic component is expected value of y is beta 0 plus beta 1 x. We need beta 0 and beta 1, our slope and y-intercept. So let's say that this is our sample data here, and we want to find the best fit line that goes down through the data. And that line actually looks like this. And the way that we are finding that line is we're finding the deviations or the vertical errors. That's y-coordinate on the point minus y-coordinate on the estimating line, which we denote by y hat. So that's called a deviation. And then what we want to do is we're going to square all of the deviations, because some are positive if the point's above the line and others are negative. And if you don't square the deviations, then you just get canceling. So we square all the deviations to make them positive, and then we're going to minimize the squares of those deviations. And we actually do that using calculus. So in other words, we're going to minimize the quantity sum of squares of error, SSE, which is the sum of the y value on the point minus the y hat value. So this is plugging into the equation for the estimating line, beta 0 hat plus beta 1 hat, and then we square those deviations. So this is the deviation gets squared, and we minimize that. So in doing that, then our least squares line, which we're denoting as y hat is beta 0 hat plus beta 1 hat x, is going to be the line that satisfies, number one, the sum of those vertical errors is equal to 0. So the mean error in prediction should be 0. And then the sum of squares of error, that SSE, is smaller than for any other line, which is just saying that we minimized that sum of squares of deviations. So you can show the following here using calculus that we won't go through. But the slope that gives the best fit or regression line is sum of squares of xy divided by sum of squares of xx, where the sum of squares of xy is the sum of x minus x bar, so that's deviation in the x coordinate, times y minus y bar, deviation in the y coordinate. And algebraically, you can show that it's the same as sum of x times y, so multiply the x and y coordinates for each point, minus the sum of the x coordinates times the sum of the y coordinates divided by the number of ordered pairs. And then the quantity SSXX is the sum of xi minus x bar squared. So the deviation in x coordinates squared, sum them up. Algebraically, that's equivalent to the sum of the x coordinates squared minus the sum of the x coordinates quantity squared over the sample size n. And then our y-intercept turns out to be beta 0, which is y bar minus beta 1 hat x bar. So once you find your slope here, you plug it in here to get your y-intercept, along with the mean of x and the mean of y. So you can think of the sum of squares of xx as a measure of the error in the x coordinate, and then sum of squares of xy as a measurement of the error in both coordinates, because we've taken the deviations and multiplied them. So let's look at an example here. We want to model a linear relationship between medication dose in milligrams and perceived headache pain y, and that'll be on a numerical scale. Here's our sample data. So we got a sample size of 4 at 100 milligrams. Your pain level is perceived as 8, 200 milligrams at 7, 404, and 802. So let's do our scatter plot here. Medication dose on the x and pain level on the y. So when x is 100, y is 8. So 100 to the right, 8 up, right there. When x is 200, y is 7. So 207. 404, right there. And then 802, 800 to the right, 2 up, right there. So we want to find the line that best fits that data. So we'll actually find the x find the slope and the y-intercept from the x and y coordinates using the formulas above. So I brought all the formulas down here, and then here's our data. Now, if you were doing this by hand, you would do something called an extensions table. So you'd add an x squared column and an xy column. And in this column, you would square all those x coordinates. So you'd get 10,000, 40,000, 160,000, and then 640,000. And then x times y, you just multiply straight across. 100 times 8, 800. 200 times 7, 1,400. 400 times 4, 1,600. And 800 times 2, also 1,600. And then you total up here on the bottom. So, but actually we can use the calculator to do this work for us and generate those totals. So go to the Stat menu and then Edit and enter your X coordinates in list 1 and your Y coordinates in list 2. Then go to Stat, Calc, and 2 variable stats. Enter. Come down to Calculate, Enter. And there we got our X bar is 375. Let's go ahead and write that down. And then we see that the sum of the x's is 1,500, so that's going to be the total on the x column, 1,500. The sum of the squares of x, 850,000, so that's going to be the sum of the x squared column. Y bar is 5.25. We need the sum of y and the sum of x times y. Sum of y is 21. And arrow down here, sum of x times y, 5,400. So now we can plug in here and get sum of squares of xy and sum of squares of xx. So the sum of x times y, 5,400. Minus sum of x, sum of y. So that's 1,500 times 21. And then we're dividing by n, which is 4 ordered pairs. And then the sum of the x squared column, that's our 850,000. We're subtracting the sum of the x's, quantity squared, so that's the 1,500 squared. And then divide by our 4. So let's go ahead and figure those on the calculator. So we've got 5,400 minus, I'm going to do horizontal fraction, alpha y equal enter. And then we had 1,500 times 21 over 4. So negative 2475. And then do sum of squares of xx, so that was 850,000. And minus alpha y equal enter. We had 1,500 squared on the top and 4 in the denominator. 287,500. And then we're going to divide the first by the second. So negative 2475 divided by the 287,500. That'll give our slope. So let's do that. Negative 2475 divided by 287,500. Oh, I got one too many zeros there. There we go. Negative 0.0086. 086957. I'll use all the decimal places in this calculation. We'll round when we get done. So now our beta 0 hat, we're going to take the y bar, 5.25. minus our beta 1 hat right here, slope, negative 0.0086, 0.86, 957, and then times our x bar, which is the 375. So let's go ahead and compute that. So 5.25. The double negative here will make a positive. So plus 0.0086, 0.86, 957 times 375. So 8.48. And then we can go ahead and round this. So that would be negative 0.0086. I would take at least 2 significant digits there. So now we've got our least squares regression line here, beta 0 hat plus beta 1 hat x. We will put that y-intercept out in front, 8.48 minus 0.0086 x. And let's go ahead and sketch that on the scatter plot here. So we know that our y-intercept when x is 0 is 8.48. So that is right here. And then we need one more point here. Why don't we pick another x value here? Because it's hard to use rise over run with that decimal slope. So say x equals 1,000. It's easy to work with. Will give us a y hat value of 8.48 minus 0.0086 times 1,000. That's just going to move the decimal place 3 to the right to be 8.6. So 8.48 minus 8.6, negative 0.12. So 1,000 to the right, negative 0.12. So our regression line will look like this. And that fits pretty nicely through the data. We've got 3 values that are above the line and 1 that's below, but this one is farther below than the 3 above.